is arriving in that river with a 3 parts per million nitrate leaching or nitrate level in it. And we're just not sure where that's coming from. And so the farmers at the last meeting said, well, all the source tracking potentially help. You know, can we try and find out where that nitrate's coming from? Because we want to make sure that any activities that we undertake will actually have an effect. So that's piqued my interest. John, you had some interest in wanting to be involved with this.
Yeah. Kia ora koutou, everyone. Welcome. Yeah, I'm Annette's colleague, John Hanson, and I'm the Trust's coordinator for Northland. Yeah, my interest in this topic really stems from the sediment source tracking studies that were carried out in the Bay of Islands catchments by NIWA and the Regional Council around 2012, 2015. And that technology really informed the work of the local catchment groups to identify targeted actions rather than just applying blanket soil conservation measures. So, you know, soil erosion and sedimentation is often presented as the biggest water quality challenge for us in Northland. But our regional sampling program really does indicate that the nitrate levels in our river system shouldn't be ignored either. So I'm really keen to hear how this nitrate source tracking technology can support our catchment groups up here in Northland. So, thank you.
We do have in New Zealand, it's fair to acknowledge that we do have some aquifers and some rivers that do have high rising nitrate levels. To solve this, what we need is farmers, scientists, members of the council, agribusiness, industry groups to come together and come up with practical solutions that are impactful and actually will reduce nitrate in those rivers. Don't bankrupt our farmers or our country. So that's what we all need to work together. So for this event, let's try and just set aside politics, you know, the hurt that's going on in all of our sectors at the moment around this, and let's be solution focused. Let's try and find, put on our Kiwi hats and find out how we're going to solve this together. First off, this webinar is going to start with a presentation by Troy on nitrate source tracking. The chat module on the side there will be running for that, so you can take Q&A sessions on that. And then we'll pause for a panelist. We can see the panelists up on the screen at the moment. And we're going to ask 3 questions. And I'll go through those questions, and I very encourage people who are attending this. We're not going to have questions on that we're going to discuss verbally. We're going to stick to the discussion, but I really encourage people to put their comments and their discussion points in the chat. We will collate them, and we'll be sending this out to all the people who registered, and we'll be trying to attempt to find answers to any of these questions as well. So that's how it's going to go, and we hope to finish by 8 o'clock. John's the timekeeper, and I'll try and sneak it a bit longer, and we'll see how we go. But yeah, to no further ado, I'll just introduce Troy, and if Troy can give his talk.
Okay, can everybody now see the screen with the slides on it? Excellent. I will try to monitor the chat. I can't promise how well I'll do it while I'm talking, but we've got a Q&A at the end of the talk, and so for questions, that's a good place to try to get my attention if you have anything that could be clearer, because I'm sure there's always something when we're talking about something as complex as isotopes that could be clearer. Let me start just by explaining who I am and how I got here to be talking about isotopes in front of you today. I am from the eastern US. I grew up in the Chesapeake Bay region, which is the world's largest estuary. My parents owned a farm but didn't operate it, about 100 tillable acres right on the water. And around the region was a mixture of cropping and dairy farming, largely. Most of the dairy farming's now sort of gone around that area, so we're still in corn, soybean, wheat rotation. I went and did my bachelor's degree in earth sciences at Dartmouth and worked in areas that coined the term acid rain, and did my honors thesis on tracing the sources of acidity that cause nitrate and sulfate to be what's called acid rain, particularly in snowfall. And then I went to Berkeley and did my PhD using isotopes to trace the carbon cycle in soils of the Great Valley of California. Then I came to New Zealand, worked on the soil carbon monitoring system, got into national nitrogen budgets, where we often tried to carry along the nitrogen and the carbon together. And in 2008 or so, I saw an opportunity to start developing this tracer dual isotope nitrate, as there was better and better methods and understanding going on in the world, and not so much in New Zealand. And so I came along and got a good source of funding from the Research for Industry program at the time. And that allowed us to really develop the method well for New Zealand. And I'll stop saying too much more about that and get into the talk, because that's where that goes. I have to say, though, it has been a winding course, and that leads me to point out that my affiliations during this time have been to be associated with the nation's biggest isotope lab or essentially the biggest at GNS Science, where we could develop methods like this, and where I went there to work on the carbon cycle a bit more with radiocarbon. There's a whole bunch of people on this initial slide who have contributed to the method over the years as we moved to different places. I was most recently professor at the University of Waikato. I'm now affiliated with the University of Auckland, but also with Molt2 Research, which is a public policy entity, with Te Puna Hamatatini, which deals with the nation's complex problems. And many of you will recognize that name as the agency that Sean Hendy was the director of, the Center of Research Excellence that he's been the director of, and got into trying to save the nation from COVID. And I think did quite a good job. That was just one project amongst many. And what we try to do is develop an understanding of how we can essentially address and fix the nation's complex problems using university-based expertise and some other parts of the research system. I also am available through a one-person consultancy called Biogeoscience now. And part of the rationale for that is that I really think we need to be trying to fix these environmental problems, not just water quality, but climate change. And we need to put together the thinking, because it all happens on the ground where you're farming at the same time, and you need to make decisions about it, and the catchments need to make decisions about it, and our nation needs to be making some good decisions about it. So that's the overall frame of this. The work at the University of Waikato was largely associated with the Bay of Plenty Regional Council's Rotorua Lakes program and the Lake Ecosystem Research Group. So a lot of it has been focused most recently on lake catchments, but the early work was focused on streams and rivers, much like the Motupipi catchment, which is just over the hill into Golden Bay, mixed geology. And that is the initiation of this talk, although I realize we've now acquired a national scale audience. I'm going to try to focus on examples that help us understand things at the scale of small to medium catchments like that. Okay. Now, with all that said, let's pick a simple goal. I think the goal we're after here is reducing nitrate contamination of water. And there's really two pieces of that that I see that we can achieve here today. The first is to identify and address the nitrogen excess and use our source tracing as one way that we can identify what excesses there are in the catchment and how we can identify them and reduce them. And the second thing about that is thinking about how to get the right land use in the right place at the right time. That really comes down to a simple goal, which is better farming and better water, better fresh water and estuaries downstream of the farms. So the idea there is that source tracking can help as part of a suite of tools, and it may fill a role that we don't currently have in action. It is not, however, a silver bullet. And so I just want to get that out of the way up front. What it is, though, is a great way to cut across this problem that farmers often have to deal, if they're starting to think about water, with not just the farming system and their soils, but they need to start thinking about the hydrology and the groundwater. And how do you even start to think about that, as well as what happens further downstream, including freshwater impacts? And so this work is aimed to connect that. In fact, one of our panelists, Simon Stewart, had in his PhD work that showed we could get all the way through from the nitrate in the Lake Topol catchment right to the basal level of the nitrogen isotopes in the food web in the entire Lake Topol ecosystem. This work goes across disciplinary boundaries, and the key thing I want to get across to you is that if you really want to get this right, the best tracer of what the sources of nitrate are is the nitrate itself. So let's just think about what nitrate is. It is a molecule, contains one nitrogen atom and 3 oxygen atoms. And those atoms contain isotopes naturally. And so if you weren't aware of that, that's the key thing that we're talking about today, is that 0.1% of the nitrogen out there and 0.2% of the oxygen are not the most common form. They're the other form that we're going to measure on a mass spectrometer by converting this molecule into nitrous oxide, which is a gas, and allows us to measure it efficiently. I'm not going to talk about the lab details, but the key thing is that allows us to look at those oxygens and the nitrogen and put them on a plot, and then start to identify which source goes where on the plot, because different processes in the environment discriminate, relatively speaking, against the rare and the common isotope. So if we think about that in just a little more detail, if we have our disciplines getting stuck in a funnel and we want them to break through into fresh water, I've dropped the molecule there and it knocked the F off of our fresh water here. But the key thing is tracers really help us if we have systems where we can't just follow water through a stream on the landscape. Instead, we need to try to understand how it's popping up in springs or even groundwater fed inputs to streams or lakes or estuaries for that matter. Okay, so that's really what we're about here, is being able to identify sources of nitrate that we can't unravel easily from what appear to be the way landscapes work when you try to draw the streamlines through the river system. And it turns out that many of our river systems in New Zealand, because we have gravels, actually don't connect. At the same time, if you look at a typical farm like this, you can't see any water flowing, and yet there may be nitrate ready to move or moving downward. And so the key thing here is we can write chemical equations for what the sources of nitrogen are that lead to the nitrate, and you'll see that we can think about what the source of nitrogen is and what the sources of the oxygen are. Turns out that the oxygen comes mostly from water in the landscape, but also partly from atmospheric oxygen. And the two are quite different. We'll talk about the atmospheric oxygen in an odd way, because it's possible for nitrate that's produced from atmospheric oxygen alone to have a very different chemical signature. And that's the nitrate that comes out of a bag as nitrate, as ammonium nitrate, for example, and is added to market gardening systems or cropping systems. Whereas nitrate that forms in soil typically will have a signature that reflects what's going on in the soil environment at the time. Oxygens will tend to reflect what's going on with the water isotopes in the soil at the time. So that's the key thing there. The time sequence of looking at this was really that we developed some initial understanding for the first 3 years. We were the only lab operating for quite a while in Australasia, and there's one at Southern Cross University on the northern New South Wales coast. It's also quite a good lab. We had to build a capability that could really do this for New Zealand, and I'll show a little bit of why that was difficult. Relatively low concentrations and high precision were required, we did it and did it well, but it does not make the analysis cheap. And so then there was a lot of gap filling, which allowed us to begin understanding the New Zealand system a lot better. And then there's been, in more recent times, a focus on what I would call hot spots and hot moments as control points in the landscape for management. Hot spots and hot moments are really interesting if you're a scientist, but it's turned out for land managers and policy people, they're confusing and distracting and not very helpful. So there's been a suggestion that we begin to think of them more as control points in the landscape, where there is an opportunity for management or understanding of where water is just going to flow on its own anyway. This is the global perspective on what drives nitrate isotope signal that people look for. A lot of the early work separated fertilizer nitrate from other agricultural sources, for example, in lakes, often, for example, as a transboundary issue at the US-Canadian border. Most or much of the interest internationally in recent years has been precipitation or essentially smog and acid rain. That has a crazy high delta 18 signature. We won't see anything like that in the plots I'm going to show you. So what we're effectively doing in most of New Zealand is crossing out these and zooming into the area of the plot down here. Here's what it looks like when we zoom in. Now, this is a little bit of a cartoon drawn to represent the types of data that we've gotten recently. When soils are working well, it actually looks like this, so that the nitrate concentrations are now shown as a bubble plot that increases the size of the bubbles, largely with the duration and intensity of agriculture. And we're also increasing the delta N15. So this is the nitrogen isotopes signature, if you will, and that means more of the heavy nitrogen isotope N15 as we go along the plot this way, more of the heavy isotope oxygen 18 compared to oxygen 16 as we go up the plot this way. Most of New Zealand sits oddly along this 1-to-1 line that goes right through here. So it goes through 0 and -4, 0 and +4, and it has the 1-to-1 slope. And I've learned to just look for normal functioning nitrate as sitting on this line between about 4 and 8, and slightly increasing concentrations over time. And that's a great question. Yeah, thanks. So what does it mean when the soil is working well? That means that when urine from a cow, for example, lands on the soil, or there's any excess nitrogen in the soil, it's taken up into the soil organic matter pool, and it's held there. And then the nitrate that comes leaching out of the soil actually looks like the soil organic matter pool. It doesn't look like those high nitrate or high nitrogen sources like urea fertilizer or animal urine that have dropped on the soil. However, if we see that, that's what happens out here. If we have a direct conversion of a cow's urine spot, excuse the American accent when I say urine, if we have that direct conversion, it will appear somewhere out here between right around 0 per mil is typically the composition of plants that are converted to urine, as well as the composition of urea that's added to soil. And that's because 0 is the composition of the atmosphere for the most part. Similarly, if we had nitrate-bearing fertilizer, the atmosphere for oxygen is about 23 per mil, and nitrate-bearing fertilizer, if it was ammonium nitrate, that's half of each. It'll come out right about here in the middle. Okay, so that's what we see there, but we can also see mixtures. So for example, when we have gravelly soils that are a mixture of this and this, we're actually going to see the brown, which is bigger in concentration, but not as big as this, and follows the same pattern of getting more enriched as we go up the chart. And we can have effluents and septic sources that sit out here. I'll show you examples of those later on. Similarly, if we had nitrate-bearing fertilizer, it can start to move in this direction, and that's a result of the process denitrification, which removes nitrogen over time from the environment. So this is one of the first plots that I produced of data from some part of New Zealand that I hadn't been working in much. And oddly enough, it included data from the Motu-Pipi catchment. We typically at the time were seeing that forest and pasture streams were sitting down here and had very low concentrations. And at the time we were aware that denitrification would push in this direction. We hadn't yet started to see that 1-to-1 line, which I've now plotted here. So there's some possibility that these are pulled off the line to the left. The most interesting thing, though, was the Waimea Plains had a site with 5 ppm nitrate that sat up here and appeared to be largely fertilizer nitrate mixed with normal sources and then some denitrification along a path. So that was one of the most interesting samples we got for years and was just, unfortunately, one sample. It gives us a good illustration, though, of how to use dual isotope nitrate to identify sources. The other thing we can potentially do with dual isotope nitrate is quantify denitrification, but it only works along a flow path. And in a way, it's been very problematic to do because it often involves confirming that nitrate has been flowing clearly along a flow path. There have been some cases where that's been possible. So I'm not going to talk too much more about that today. That's a fun argument to have with scientists, though. There are some key assumptions involved in this. So the main one involving sources is that we really are looking at different sources mixed together. The key assumption is actually that the denitrification does indeed disappear, because if it disappears along a flow path and then we mix it together with high nitrate sources, we really don't see the denitrified signature anymore. It actually disappears because this follows mass balance. And so what really matters is what's leading to the highest concentration. So that's an assumption that works in our favor. Now, we had a lot of early data that was potentially problematic, but we also had a lot of data over time that taught us a lot of things and has really showed us what we can do with sources. So let me jump back down to some of the early data. And this, I think, was fun. So this is really just taking through the story of the way we found the science here. So this is the Upper Manawatu catchment, which is actually becoming quite forested now, as I understand it, but was at the time New Zealand's most pastoral catchment. So this is the part over going north along the Manawatu River from the Manawatu Gorge. So we see the streams coming out of the forest. Again, these are the same axes where we have nitrogen isotopes here, oxygen isotopes here. We've got the less intensive sheep and beef country, more intensive dairying country on more gravelly soils. And then interestingly, we've got the main stem of the Manawatu River. And what you see here is that the main stem of the river is a mixture, as you'd expect, of everything else in proportion to its concentration. We also have the effluent derived from the PPCS freezer works effluent ponds. So that was denitrified and pushed out well to the right. So that's an example of source tracing in action. And another source that is traceable is what turn out to be sewage treatment plants that have photosynthetic activity. They lead to samples that sit off the bottom of these types of plots. So source tracking works there. A next logical place to go to try to understand things in more detail closer to GNS was the Mangatariri catchment. So this is just outside of Carterton in the Wairarapa. And interestingly, it's cut by a few faults. So here's a scarp right on the Mangatariri River, which is defined by one of those faults. And we sampled a number of inflows as well as just a nice little stream. We could walk up and down the stream with students in the summer and actually construct a plot that showed us how, as we went by different sources, including one of the nation's largest piggeries, we could see what was actually happening and what water was coming in and out of the stream over time. And at the very bottom, we had the wastewater treatment plant. So here's a schematic of what that looks like. There were 2 faults, and the piggery actually sits right on one of the faults. The groundwater flow direction feeds the stream down here and cuts across sewage and old, largely unknown landfills, or the wastewater treatment plant areas. So this was very interesting, and what we saw was that the delta N15 nitrate goes shooting up and starts looking like piggery effluent after we cross through the piggery area. But it actually goes back down again quickly, and then has some changes perhaps after we get to the Carterton fault. And in fact, that's when the nitrate concentration goes up the most. We see that the delta 18 off of that line that I've been plotting, off of that 1-to-1 line, also takes a bit of a jump there. The precision of our analyses is better than 0.5 per mil from all this work. And we can also begin to look at water isotopes and see that there's a big change in the water. So over a couple kilometers, it appears that we're really changing the water in this river, and that conventional council water sampling networks along the stream system don't capture that well. And again, we also see that in the as we go past the sewage treatment plant and landfill areas, we can see that there appears to be some evidence for increasing signature, diffuse signature, and getting back to very high values that look like effluent, and some change in the water isotopes and the nitrate concentrations associated with that, but not particularly clear. Now, I thought I had it understood at that point and was ready to start publishing it, but all these samples had accumulated in the lab from Southland. I'm only going to show you a few of them, but I think this is a good representative set, and it also leads to my point about how what they were doing in Southland led to understanding that allows us to think about how to run farms to put the right land use in the right place at the right time by having an integrated understanding of the landscape. So in Southland, they were beginning to plot some different, what are called physiographic zones, and these were the Southland physiographic zones that Clint Rissman and his team had developed at the time. So we'll start with the oxidizing, which is basically our gravel soils, typical young gravel soils. You see that relatively few of them are sitting here in the normal nitrogen retention that I've talked about. So that's where the soil nitrogen pool is capturing nitrogen that's added and then releasing nitrogen that looks like the soil in terms of its nitrogen isotopes. Instead, what we're seeing is a lot that's coming through below 4 per mil and in big concentrations. In a few cases, we also saw effluent coming through. In contrast, glade soils, that is to say your heavier soils with reducing character, had lower concentrations, and they hardly had any that came out down here unless it perhaps came out as overland flow or looked like it was from a fertilizer source. Really interesting thing down there was there was the old highly weathered eye. It appeared and confirmed the classification of landscape elements that are mappable and can be used to help people understand how nitrate moves through landscapes in very different ways, not just at the soil, but at the landscape and hydrology and groundwater level. And in support of that, we had, there were some soils there that have cracking behavior so that large macropores form at the times of the year when nitrate can pass neatly through the soil. And so you can see that behavior as well. And that was in the Central Plains area of Southland that has both animal agriculture, particularly dairying, as well as cropping. Now this physiographic zone approach has led to the development of a tool that you can go and look at landscapedna.org, where you can look at the science, and I'll particularly note that there's some really good videos available in there. You can also go and look at the maps. So let's have a look at what's possible in terms of maps here. So this is what these units look like classified into a series of units that are useful for not just nitrate, but understanding all your major contaminants nationally, and include some other issues like natural bypass flow and whether or not parts of the landscape have drains in them. If we zoom into the area around the Multipippi catchment, we can highlight a particular catchment, see that it contains hard bedrock up here, and for example, oxidizing soils and aquifers, which are the equivalent of that oxidizing unit. In Southland, there's other reducing units, riverine units, and particularly oxidizing soil over reducing aquifers. Nitrate is consumed by reduction. Nitrate is effectively an oxidant that replaces oxygen as the next step in oxidizing anything like organic matter in the environment that needs to be oxidized. The only problem with that is it may produce nitrous oxide, but that's one way to get rid of nitrate that's extremely valuable. And so this helps us understand where we have reduction in landscapes at a broad level, and it puts it all in one tool, so you don't need a separate soils map and a separate geology map and a separate hydrology classification in order to begin to understand what's mapped in a particular area and begin to correlate that with more detail. That's what's mapped on a farm and what could be included in a farm plan. Now, I mentioned that I try to rip through also hot spots as well as hot moments. So let's think about hot moments for a moment. This is the Okaro catchment, which is the smallest of the Rotorua Te Arawa lakes. So up on the central plateau, the North Island at relatively high elevation. The lake's a bit over a kilometer or so across, and it has a small but fairly simple catchment. And you can see here that when we monitored a number of events, we could see that the urine and urea fertilizer signature was shooting out during the events, but there was also a lot of time when we saw good retention of soil nitrogen within the catchment. The key thing here, and this is what I'd like to get you thinking about, is that if we monitor events at a scale that matters, we can use hydrograph separation done using water isotopes to understand, here's the rainfall. You can see the peak rainfall is followed by peak water that's from that particular event. And that water from the event has lower conductivity, that is to say less salts in the water, and it has a change in the isotope signature. And more importantly, it has changes in the nitrogen concentration. So the nitrogen concentrations go shooting up in the event, as well as the nitrate concentrations. And the dual isotope nitrate signature goes down from the typical values that I've talked about as soil retained nitrogen signatures to urine and urea signatures shooting out during the event when we're seeing the most flow. So they disproportionately account for a lot of the water going into the lake. When we look at it on an annual basis, we can actually begin to see that the water isotope signature follows a seasonal pattern, but that a lot of the changes during events don't follow the smaller seasonal pattern we see in the stream. They are chasing that particular event, and they allow us to pick out, using a special kind of plot, the idea that many of our events are mobilizing our contaminants. And that's what we want to understand, where to get these big bubbles. The concentration of mobilized events compared to events that are just diluting the water that's in the catchment. So again, that catchment also showed that we had these big hot spots of urine and urea shooting out. So the first thing we can see there is there are particular times and particular soils where it is not helpful to be seeing that. And there are essentially two things to think about it. One is what can we do at the landscape level? And the second thing becomes what can we do at the farm system level? I'll just take you through maybe one more quick example. This one's about 30 seconds. I can't actually see the talk too terribly well right now. So, oh yeah, I can see the chat, but so what I'm going to do here is reverse this and just start it over. So this is that one-to-one line again. So this is where we typically see good nitrate retention, and that was only seen in the urban catchment around Rotorua. Out here we see the wastewater treatment plant. Over there on the left we see geothermal sources. And then we see most of the inflows to the lake follow a similar pattern. And it's a pattern that's well to the left of the line. And so what that means is that we've had urine and urea breakthrough, much like we saw in the Okaro catchment or in Southland, but it's coming out far to the left of the line, and it is moving through groundwater, which moves slowly into the lake. And so the opportunity to improve this system is to try to understand where urea and urine can be reduced. Similarly, we can look at things in time in Southland. And I just want to point out, this is an example. I'm not going to show you from the data, but Ray McCrosty and his son and some other colleagues, along with Clint Rissman, have been building a system that actually goes into a tile drain in Southland. It's gotten a fair amount of media, and we've got data from that, which has been really interesting. And so this is an example where farmers can get involved in monitoring. And it's a really great collaboration with scientists that leads to some interesting conclusions. And at the scale of the Waituna catchment, what we were seeing was what appeared to be oxidation of some of the organic matter in the catchment, and that led to another unique source of delta N15 and nitrate, with relatively high values that looked like effluent, but was probably decomposing organic matter. I'm going to finish moving on now, and sorry for the many interruptions, with the idea that we could actually work with some international principles. Now, one of the top reasons to work with international principles is that our markets where we sell products care about international principles, and they care about seeing them carried into the supply chain. So the first one is that nitrogen inputs and outputs actually do have a balance, and what goes in must come out. The great thing about isotopes is they work directly in proportion to mass balance. So for example, where genetic tracers are really good, they don't follow mass balance, whereas isotopes do. And the key thing there is we have inputs and outputs, and what comes out into water is easily visualized, as well as what comes out into the atmosphere and represents nitrous oxide as something that can be reduced and potentially accounted for as the emissions trading system starts to bite. It's an opportunity as well as a problem for farms at this stage. Moving backwards from principles 7 to 5 and 6, we really want to think about how nitrogen can be controlled at an input level. Now, there's been a lot of disinterest or fear of having input control at a regulatory level in New Zealand. I think the right level to think about input control is on farm for the reasons in these two principles. If we can identify nitrogen excess and cut it back, if we can identify that a good level of pasture nitrogen is around 2 or 3%, typically closer to 2%, and if animal intake's exceeding that, it leads to that excess going into animal urine, particularly in the winter is when we have those high nitrogen concentrations. So feeding out silage, alternative pastures like plantain, those are all opportunities there. If we don't do that, then we simply get into the situation where trying to back up the system further down the chain leads to backups, which lead to nitrogen coming out in other ways. And one thing we did see in this project was attempts to convert nitrate out of the system going into lakes may have simply led to ammonium and particularly organic nitrogen going into lakes. So, overall conclusions. Dual isotope nitrate tags are nitrogen sources. Here's a list of some of the better ones. Water isotopes are also useful, and they're much more cost effective, along with tracers like conductivity. Temperature even is a good tracer. So these other tools and our understanding of the landscape are critical for making use of these source tracking tools, which are not silver bullets in their own. Previous development has been aimed at typically policy scales because that's who we thought could pay for this work. The tools are now relevant to farms and catchment communities at the scale and costs that changes probably need to be made. I think what our biggest limitation, and this is where we'll head next, is thinking about what science is needed and what level of accessible experts are needed to engage with farming communities around their farming and freshwater. So just to emphasize this overall story, if we're going to reduce nitrate contamination, source tracking creates an opportunity to identify and address nitrogen excesses and get the right land use in the right place at the right time. And that's an opportunity for better farming and better water. Thanks.
Thanks, Troy. So trying to just summarize what I think I've just seen is that you can track where the various types of nitrogen are coming into the water from different sources, and that might change over different times. And what wasn't clear for me is, can you quantify the amount of nitrogen from those sources?
We can up to a point. So if there's two big blobs that overlap, we can identify what sits in which blob. If there are two sources which are separated a long distance across that space, the proportion of each source is exactly how far you are between those two sources. But if they're two big blobs, both the blobs are so uncertain that the distance in between also is uncertain, if that makes sense. So it literally is quantitatively how far you are across one of those plots represents the proportion or mass of nitrate or not the contaminant that we're dealing with.
Excellent. Are there any other questions that people have on what we've just seen?
There's one for you there, Troy, from Elizabeth. Can you discriminate effluent between human and animal?
No, generally not. We might be able to tell better if people are vegetarians or animals are vegetarians versus on the extreme end of eating sources of their diet with high nitrogen. So that is actually commonly done as an archaeological tool, is to use nitrogen isotopes that way. And Simon there did his PhD showing that you could watch the nitrogen accumulate up food chains in, for example, Lake Topol as well. So you can tell certain things about diet, and there are some opportunities, but they're mixed in with the wastewater treatment or septic processing as well. So that's a good example, I think, also of why the tools are not perfect, and they're not silver bullets, but effluent sources do look very different than animal urine, and it's a direct form. It looks remarkably like grass. Whereas manure and effluent sources from the dairy shed effluent, for example, look quite different. They look out to the right of the plot.
There's no more questions in the chat right now, but I've got one for you, Troy.
Great.
And what I'm wondering is, how accessible is this technology to, say, a catchment group out there somewhere in New Zealand, if they were wanting to use this technology? How would they get started, and who would they approach?
Great question. So, since I've been one of the main developers, I'm a pretty logical choice. There are certainly some other people that are reasonably familiar with it. So GNS can be approached, especially if you know what you want to do and want your samples run. Simon, who's with us tonight, has been somebody who's at Cawthron and did his PhD. So particularly if you're in that region, I think that's more of what I'd like to see. At this stage, what I'd like to see, I guess, is really us starting to build up some people with regional skills. And we can think about whether some of our council scientists are the right person to trust for that, because that would be a great place to build some skills in each region that has a diverse set of nitrate sources and can be differentiated. Catchment group managers are potentially capable of it. You'd think not the average catchment manager would be in that category, but for example, I have one PhD student that's gone off into those sorts of roles that worked on this type of technology. So you never know. I'd ask around and see who's comfortable and has a little bit of an isotope background, and I'm happy to help try to find those people or jump in myself. The trick has been very much trying to identify what it's going to cost to get started and think through what the sources are. And at least with 12 years behind us, a lot of the mystery of what we're going to find is hopefully behind us.
Yeah. Okay, and I've just been alerted to there was a second part to Elizabeth's earlier question, which was, I think she had said, and what was that bit about decomposing organic matter? So can you clarify?
Yeah.
that?
So that's a pretty interesting tidbit. I can see Elizabeth being the type of person that would get interested in that one. So where we do have a store of organic matter around coastal Southland, for example, or other areas with drained wetlands, it makes sense that some of that's decomposing and releasing nitrogen as well as carbon to the atmosphere. And some of that will be old, and that is essentially what we're seeing. What we need to do is start thinking more about how to take that into account in nitrogen budgets, including overseer.
Okay, I'm conscious of time because we had a bit of a delay, but just there's one more in the chat there from Mike Campbell, and he's just asked, so to ensure I've got a good handle on the concept, you can track the source of N based on ratio of the two isotopes. Does Mike have a good handle? He's got the thumbs up. Lovely.
Absolutely.
Okay.
Yeah, so that delta value is the ratio of the two isotopes. And it's presented in per mil, which is like percent with an extra zero on it. It's literally parts per thousand. So it's a small change, but for the labs that can do it well, it's easily measurable.
Excellent. Well, I think we'll move on to our discussion section.